Right, good morning, folks. Are we live? Can people hear me okay? My name is Ivan Tolson. By day, I work for Green Button. We're a provider of cloud platform for high-performance computing, for intensive computing in Windows Azure. But by night, I don a cape and fight crime. Fortunately, my area is not terribly high in crime. Famous last words, my area is not terribly high in crime. So I also get the chance to learn about lots of interesting new programming languages. And one of the languages that I've learnt about over the last few years, and that I've used in production a couple of times now, is the F# language from Microsoft. F# was introduced about 5 years ago and made it into Visual Studio as part of Visual Studio 2010. It's now an open source project run by the F# Foundation, driven out of Microsoft Research, but with other people participating in a very active community around it. And one of the things that I struggled with when I tried to figure out how F# fitted into my workflow was that about the time that F# was coming out, C# and Visual Basic were gaining a lot of the features that people told me were key to functional languages. This was about the time frame of LINQ. And LINQ was really a big move towards a functional style of design within the C# and Visual Basic languages. The LINQ operators use this concept of higher order functions, that is, functions that take other functions as arguments. So if you think about something like the LINQ where operator or the select operator, the where operator takes a function to Boolean as one of its arguments. The select operator takes a mapping function as one of its arguments. And so these languages, Visual Basic and C#, already provide a lot of the benefits that a functional language is supposed to provide, the sort of the expressivity, the composability of these functional languages. And before I dive into F#, I kind of want to illustrate that by comparing the imperative style of C# or Visual Basic to that functional style, because I've learnt that, to my surprise rather, a lot of people are actually not using LINQ day in, day out, and don't really see what it's giving them. So I want to illustrate this, first of all, just by showing you a couple of functions written in imperative style. So here is a function for calculating the product of all of the elements in a list. You can see it's pretty simple, pretty easy to understand. You can follow it through, start with an accumulator, go through the list, multiplying the accumulator each time, return the accumulator. Here's another function, sum, which sums all of the elements in a list. You can see that's pretty easy to follow as well. You start with an accumulator, you go through the list, adding things to the accumulator, you return the accumulator. But if you look at those two functions, they actually look really similar. In fact, in a night of particular boredom, I counted how long those functions were, and they're about 90 characters each. And of those 90 characters, 2 are different, and the other 88 are the same. So when you look at those functions, it's actually a little bit hard to see at a glance what they're doing and what the crucial difference is between them. What is the similarity? What is the difference? In a functional programming approach, we would have a concept of an aggregation operator. And the aggregation operator is encapsulating the idea of we're operating, we're accumulating stuff over a list. Similarly, you can compare that to, say, a filtering operation. Here again, I've got to read through the code to understand what it's doing. In a functional programming approach, I've got, say, a select operator, a mapping operator, a filtering operator, an expand operator, and I can express things in a much more declarative way. So have a look at that product and sum example in LINQ style C#, in functional style C#. You can see that, firstly, each one declares very clearly I'm an aggregation operation. I'm going to combine all of the contents of this list in some way. So you know how they're similar. You can also see very clearly how they're different, because there's a lot less stuff to look at here. You can see the differences are, firstly, the starting value of the accumulator, and secondly, the operation that happens as each element is accumulated. So by using those functional link style idioms, we can see the similarities and differences between functions a lot more clearly. We also gain the ability to compose this stuff much more readily, which again helps with readability. Those functions we saw were simple, single-purpose function. They were only doing one thing on the list they were operating over. What happens when you're doing several things on that list? Well, the imperative style, those different things get mixed up. They get combined into that same method and make it a little bit harder to read. So here, for example, is a mystery function written in the imperative style. What does it do? Any guesses? Sorry? Sums up the squares? Sums up the square roots. Anything else that it does? Sums up the square roots of the positive numbers. So how do we work that out? Well, we have to actually we have to either recognise idioms in that noise, in all of that code, or we have to actually run through it. When I have to figure out a function like that, I end up having to run through it in my head, mentally going, right, what am I doing here? What's happening as this goes through? I'm running a little mini compiler in my head. If I compare that to the functional way of writing the mystery function, you can see, because we pull out those filtering and mapping and summing operations into separate explicit steps that declare their intent, you can see that they are much more composable, it's much more easy to read. There's a lot less cognitive burden to understanding what that code is doing. So LINQ has given us a lot of the benefits of functional languages within our mainstream C# and Visual Basic languages. But given that, why am I still interested in F#? Well, I think there's a lot of things that the F# language has that are not part of C#. Even though C# has made that huge dent in functional languages, although it's given you a lot of that capability, I think there are a lot of things where F# has a little bit of an edge, and that makes it still worth investigating for some of those scenarios. And what I want to do today is just run through 10 of the things. Well, I say 10, it turned out to be 17, so I had an off by 1 error for large values of 1. And just show you some of those things that I think you might find attractive and useful about F# for some of your applications, some of your projects. Well, one of the distinctive features of many functional languages, including F#, is that pretty much everything has a value. Everything is an expression rather than a statement. So let me show you what that means. So let's take, for example, the switch statement in C#. Can people see the text okay? I'm not sure I can make it an awful lot bigger. Are people at the back okay with the font size? You need it bigger? Okay, make it a little bit bigger. This is going to get troublesome when I show you how verbose C# is and how long the lines get. I may need a bigger projector, but we'll see how we do. So, switch in C# is not an expression. It does not have a value. Therefore, the only thing it can affect anything outside itself is by having side effects. So, if I want to convert a number to a piece of text using a switch, I have to declare a variable outside it. Then, in my switch, I will assign that variable as a side effect, and then I can do something with that variable. So you can see I've acquired a little bit of verbosity there. Whereas in F#, the nearest equivalent, and we're going to see a lot of this, is the match expression. Now, match is an expression, not a statement. It has a value. What value it has is determined by what case you end up in. So here I can just assign this variable to the value of the match expression and use that value directly. No side effects. No updating that variable separately from declaring it. Another example of that is, excuse me, with exception handling. Again, you've got that same pattern of I have to declare a variable outside my try-catch block, and then because the try-catch is a statement, not an expression, the only way I can do anything with that variable is by modifying it with side effects. In F#, try with is an expression. It has a value. If the try all succeeds, then the value is the value of the try part. If an exception fires, then the value is the value of that catch part, effectively. It can still propagate exceptions still further, but the point is I can just let text equal try this with that. I don't need to have side effects involved. And this is quite a common pattern in functional programming. Sorry, could you say a bit louder? If you have more than one exception type you want to catch there, we will just add another clause. Okay, it's telling me that's a stupid clause to have in there, but you get the idea. You can just add more. It's a catch clause. It's always going to be exception. We could make it something like that. So there we go. You can have multiple kinds of different value coming out of that. Does that answer the question? People comfortable with that? All right, so that kind of raises the question of, well, if everything is expression and everything has a value, what about things that don't have values? What's the value of console.writeLine? Well, you might think that's kind of a weird academic question, but actually it turns out to be relevant because, and this is where I have to say nice things about Visual Basic. Are there any Visual Basic programmers in the audience? One or two, awesome. Okay, Visual Basic is officially awesome. Yay! Let's hear it for Visual Basic. So, not enough. Not enough to keep saying nice things about Visual Basic. That's it. You've had your lot. So, in Visual Basic, we have two kinds of procedure. We have subs, which don't return a value, and functions that do return a value. And C#, in tradition of C-type languages, says, we don't need all that syntactical complexity. We'll just have a special return type of void. And a function doesn't return anything. We'll just give it a return type of void. Life is good. Sadly, life is not good because void is not a type. And we can see this if we want to do something like a with exception logging function. So here, for example, I want to get a square root, but I want to put that in an exception logging wrapper so that if an exception occurs during that, I can log that, but I can still return the value from it. So the with exception logging function is pretty simple. It takes a func of t. It tries to return the result of doing that. If it gets an exception, it catches it logs the exception and throws it. That's great, except what if I want to do a console.writeLine inside that with exception logging? Well, if C# were telling the truth, I could do that. And we learn that C# is not telling the truth. Void is not a type, and I have to use a different delegate type. I have to use action instead of func for things that don't return values. Visual Basic told me the truth, C# lied to me. And as a result, I have to write this stupid overload that does exactly the same thing, except it doesn't return a value. Nice, because I love writing things twice. Well, let's have a look at what F# does. There's our with exception logging function, and there's us using it in a function context, and there's us using it in an action context, and there's no overloads going on here. Why is that? Because in F# there is a special type called unit, and unit is that no type, except unlike void, it actually is a type. It actually has a value, it can be passed around. So if I... Why do they call it unit and not void? That's an excellent question. If I had a prize, I would give you a prize. What I cannot give you is an answer. I suspect the reason is inheritance. F# is descended from a language called ML from the 1970s. And I suspect, I don't know ML, but I suspect it probably used unit. I think that Haskell, which is another functional language, uses unit. I think the people who designed F# decided to follow that functional language inheritance rather than the C# inheritance or the C inheritance. So if I look at this with exception logging, this right square root function, you can see that is a function from unit to unit. Unit is an actual type. It is just a function, and therefore I can pass it to with exception logging. I keep forgetting to my slides. There we go. There's a slide. That was worthwhile. Okay. One of the features that kind of ties in with this functional approach, the idea that things are functions, they take values, they return values, is the idea that values are immutable. And there's two kind of aspects to this. Firstly, when you define a type in F#, it will by default give you an immutable type. And this is because of this concept that things are values. So, for example, if you have a point type, suppose you have the point 1, 0. Well, in C# you might write that as a mutable type. So you could go myPoint.x equals 2. And this is kind of worrying, because what you're saying is that the point 1, 0 is now the point 2, 0, which is kind of weird. Let me give you another example. Suppose we've got a model of people, and we decide we're going to make height a full-blown type. So rather than just recording it as a decimal, we're actually going to record it as, say, a value plus a unit. So maybe you and I are both 2 meters tall, so we both have the same height object of 2, meters. And then somebody sort of comes up to me and says, "You're not 2 meters tall. You're not even close." Well, that's easy. We will go Ivan.height.value equals 1.7. This is not so good for you, because suddenly, because we've changed that height object, you, who have that reference to that 2 meters height object, you have just shrunk by 30 centimeters as well. And this is quite bad, because now your trousers will not fit anymore. It's just, what we actually want is to create a new height, 1.7 meters, and I'll be given that 1.7 meters, and you will keep that 2 meters. The 2 meters itself will not change. What we'll get is a different height. In the same way that when we we can't modify an integer. We can't take the number 17 and modify it to be 20. It's not possible. It doesn't make any sense. And the same thing is true by default with F# types. So if I declare this point3d type, that is immutable. I cannot, for example, modify its x value. What I can do is I can create a new point with a different x value, but that will not be the same. That is not accomplished by modifying the existing one. It's accomplished by creating a new one with a variant. Now, if I try to do that in C#, it makes life very difficult for me. So here is part of point 3D in C#, and you can see we've got quite a lot of stuff, and because they're values, we need to handle equality correctly, and because we have equality, we also need to handle having a hash code. That's about 50 lines, after which I lost the will to live. F# does give you a bit more stuff than that, but that's the core of it. So what C# requires 50 lines to do. So you can imagine if you're writing that, at some point you'll go, I can't face any more of this. I'm just going to write public double x get semicolon set. I'll just make it mutable because it's easier. And at that point, you are lost. You are doomed. The other thing that dooms you in C# is the fact that variables are. I was being told tell more stories. Let me tell you a story. I was working on a piece of green button code a few weeks ago, which accepted a file descriptor, essentially, with an optional timestamp. And I wanted it to do some special handling if the timestamp wasn't supplied. So I added my special handling, and I fed in a file descriptor without a timestamp, and my special handling didn't run. I thought, oh, well, I've got the test wrong. I'll have no, that's checking for doesn't have a timestamp. Okay, am I passing in the right thing? Yeah, I'm passing something without a timestamp. What's going on here? Well, fire up the debugger, step through the code, step. Oh, somewhere in the middle of this function, some helpful chap is already checking for a missing timestamp and filling it in. Rah! So now, of course, my logic will never fire. I now have to capture, was the timestamp missing at the top of the function, and check my little flag later on. And the reason I got fooled by this is because I thought, the data enters at the top of the function, I'm going to have that same data at the bottom of the function. But no, because it was a mutable C# class rather than immutable class, it bit me. So just an additional thing on that. Variables by default are immutable too. So again, this helps with that thing of reasoning, knowing that once that variable's been assigned, it's going to keep its value. You can override that, so you can say let mutable like I've shown there, at which point you can override its value. But at that point, somebody reading your code has got a warning flag saying, keep an eye out for this one. This one is about to do something sneaky. Discriminated unions are the other main sort of native F# or idiomatic F# data type. So we've seen these record types, which have a sort of single shape. They just bind a set of fields together pretty much. But what happens if you've got the case where you need to have different cases, different shapes of data, like in a class hierarchy? And an example of that is, suppose that I'm writing, say, a little calculation engine. I want the user to be able to input Excel-style formulae, and I'm going to perform calculations on those. Well, I'm going to need to have some sort of object representation of the formula that the user has entered. I'm going to need to parse it into a set of objects, which I can evaluate, and the usual term for that is an abstract syntax tree. Here I've got a very simple example of that language, and it's got 4 possible cases. The user can provide a numeric literal, they can provide a variable reference, they can provide a function applied to a list of other things, or they can provide an infix operator like plus or minus applied to 2 other things. And you can see, by the way, that is recursive in that a function application can take any of these node things. Similarly, with an infix, it can take any of these node things. So you can actually build up, a function call, and then we can add a function call contain a variable reference, and we can then add something to it. You can get a tree of these things. But notice how concise that is to declare. Again, let's just compare that to the nearest C# equivalent. So we have our base class that we can use polymorphically, expression node, and now let's declare the various cases of it. Well, there's numeric literal, there's variable reference, there's function application, and you can see that compared to the F# structure, it's much more verbose. It's much more typing to do. Another difference, which can be a benefit or a burden, is that in C#, that hierarchy is open. Because I've just declared that abstract base class, somebody else can come along and add their own derived classes, which may be a desirable thing. You may want to keep that hierarchy open so that people can derive from it. But if you just want to have a finite set of cases that are predictable, that you understand and that you can work with, then the F# approach, where they are all declared just as cases of that type, is actually a bit of a lifesaver. One reason it's a lifesaver is that in C# you've got this idea that because these derived classes are full types and can have members of their own, we can put, say, that eval method, the one that evaluates the node, into the base class as an abstract method, and we can then implement it on each derived class. And that means that if somebody else decides that they want to add a new subclass, they can just implement that abstract method. In F#, the only actual type in play is the expression node type. These cases are not types in themselves. They are simply shapes, they're simply cases of that. So when we write a method, it has to operate on an exp node, or an expression node. So how do I deal with those different cases? Well, that's where this match keyword comes in again. We saw match earlier acting as a switch statement, but match is actually a lot more powerful than that. Match is a general pattern matching capability. So when I say I want to match this expression with these different cases, F# will build code that goes, well, is it numeric literal? If so, I will pluck out the value of that numeric literal into the variable n, and then I will do whatever is on the right-hand side of the arrow. If it is a variable reference, if it is that case, I will pluck out the name into this variable v, and I will do whatever is on the right-hand side, and so on. If you're familiar with the visitor pattern, this is kind of similar to that. And this is why discriminated unions have to be closed, because you can't, the way you add new methods to them is by writing functions that do matches like this. And if you don't know the full set of cases, you can't write a function that's guaranteed to cover every case. Pardon me. So once again, this is a very concise notation. It's a very controlled notation. One feature of both record types and discriminated union types is that they are non-nullable. We've probably all grown up on C, C#, C++, Java. We kind of take null as a fact of life. It's like earthquakes or volcanoes or hurricanes, and slightly more destructive. It is not actually a natural thing. It was invented by a man called Tony Hoare in the 1960s. He has since called it his billion-dollar mistake. At current estimates, he is pretty badly wrong. I think the current estimate is running at about $1 billion per year. The reason that null is so deadly, the reason that null causes so much damage, is because it can sneak in wherever you're using a class type. You always have to worry about, whenever you see a function that returns a string or a point or whatever, you don't know, is it actually going to return me a string or a point? Or could it return me null? this weird no value case? Well, F# has good news for you. If you don't like writing repeatedly if such and such equals null, F# will save you. It will refuse to even compile code that mentions null. You cannot return null as a value. Thank you. You cannot return null as a value. Yes! All right, now we're getting somewhere. Similarly, you can't even write comparisons to null because F# types can't have the null value. Incidentally, if you're interoperating from F# to the .NET framework, so with non-F# types, F# admits, okay, they can be null, and it will let you write this stuff. But as long as you're operating within the F# type system, within the F# language, rather than interoperating, no nulls, no null checks, nothing to worry about. You may have spotted a small problem with this. What happens if this method can't get a point out? What if we do need to say, I don't have a point for you? Meet the option type. Option is a built-in F# type. It's actually a discriminated union, like we saw earlier. And it's got two cases. It's got some and none. So when you use the option type, you're saying that there are two possibilities. Firstly, I've got a value, and this is what that value is. Or, I don't have a value. So here, if I've got this successful parse, I'm going to return an option of the sum case, which says I have got a value, and this is it. If I can't parse it successfully, I'm going to return the none case. I didn't get a value. At this point, you may be thinking, why, Tolson, you knave, you hound. You've made all this noise about kicking null out through the front door, and now you've sneaked it back through the back door. By Jove. Well, no. Let's have a look at the signature of that parse point 3D, where we could see that returned a point 3D, guaranteed. Whereas this, if we look at that, it returns an option of point 3D. So when I'm calling that, I have to deal with, I can't just access point.x or whatever. I have to somehow get the point out of it, if there is one. And again, I can use that match idiom. There are also a lot of helper functions to make this so make it less verbose. But at the lowest level, I can use this match keyword, and I can say, well, in the none case, I don't have a value, so I have to do something. In the sum case, I do have a value. It's going to get pulled out by the match expression into the point variable, and now I'm guaranteed that point is an actual point 3D. It's not an option, can't be none anymore, it's guaranteed to be a point, and I can party on it. Until you've partied on a point, you don't know what partying is. Incidentally, if you want to, sometimes you want to say a bit more than just I have a value or I don't. You may want to say I have a value or I have an error, and this is my error. In which case you can use the choice type that's built into F#, or you can create your own errorable or failable or whatever type very easily. It's just a discriminated union. All right. Type inference is something that's kind of a little bit tricky to show, in that I've kind of been showing it all along. We've talked about types a great deal, they've not actually appeared very much. So, for example, if I look at this this parsPoint 3D, well, you can see I've had to say that it takes a string, but somehow F# has worked out, if you look at that tooltip, the compiler has somehow figured out that it returns an option of point 3D. This is in contrast to C#. In C# we can use the var keyword for local variables, and C# will infer the types. You can go var I equals 17, and C# will figure out that I is an int. But if you try writing, if you try using the var keyword in a function signature, then C# will rapidly get very angry indeed. So oops. You can see it's not going to let me do that. No matter what body I fill in there, C# will require me to explicitly declare the return type and the argument types of my function, whereas F# was actually able to work them out most of the time. Like I say, sometimes we had to provide it with a bit of help, but mostly it was able to work them out. And rather wonderfully, this extends to things like generic type inference as well. Here is a declaration of the link select function in C#. It returns an I-numeral of T result. It has two generic type parameters, T source and T result, and it has two arguments, an I-numeral of T source and a func of T source T result. You can see there's quite a lot of text there. That is column 119, even allowing for the indent. That's quite a long declaration. Let's compare that to the same declaration in F#. It's a little bit more concise. And yet, if I go and hover over that, you can see it's figured out that it is a generic function. Those little ticks are generic type parameters. It's saying it's taking a function from one type to another and a sequence of the first type, and it's returning a list of the second type. It's able to work that out from the body of the function, and it's able to figure out that it's not bound to ints or strings or points or whatever. It will work with any types. It's a generic function. This is also a nice way that it works incrementally. So if we look at a C# function to print an element of a dictionary, I have to use this T key, T value all over the place. In F#, well, because it's using this .try get value, F# can't work out just from the fact that it's saying .try get value that it's a dictionary. So I have to give it a type hint. Like that. But I can put in these underscores that say, you're so smart. You work out the type parameters. You figure it out. I'm a busy man. And it does. If we look at that print element signature, you can see it's figured out that, for example, key has got to be the same type as the first type parameter to the dictionary. One feature of F# that kind of feels small and trivial at first, but actually becomes quite powerful once you start to really leverage it, is the ability to use infix notation, the ability in particular to define your own infix operators. And I'll start off with a very trivial example of that. I can define, for example, a double plus operator. And I can say that's infix just by encapsulating it in brackets like that. And here I'm just using it to join two words with a space. And again, you can see F# has inferred the type of that, and I can then use that as an infix operator. If I compare that to the closest I can get in C#, you can see it's kind of not as pretty. I end up with something a bit more verbose. I can overload existing infix operators in C#, but in F# I can define new ones, whole new ones. Where this really takes off is the ability to get into internal domain-specific languages, so sort of little mini languages within F# for particular tasks. And I want to show you one called fparsec, which is a library for parsing text. So I'm going to use that kind of calculation example again. And I'm going to show you some parsing for that. So, for example, here's a declaration for a list of expressions separated by a comma. And most of this looks like kind of normal functional declarations. That's saying match an opening bracket. That's a function that matches a closing bracket. And this function creates a parser that matches a list of expressions separated by a comma. But we've also got these funny arrow operators. And these are infix functions defined by fparsec. And this one means I want you to match the thing on the left followed by the thing on the right, but I'm only interested in the thing on the right. Similarly, this one means I want you to match the thing on the left followed by the thing on the right, but I'm only interested in the thing on the left. So you've got this quite mnemonic operator design where you've got that double arrow symbol to indicate this is a sequence of things to match, a sequence of parsers to match. And the dot moves from left to right to tell you which side I want to keep. So what this is saying is I want you to match an opening bracket, then a comma-separated list of expressions, then a closing bracket. But those brackets I'm not interested in. The only thing I actually care about, the only thing I want you to tell me about as the consumer of this is that thing in the middle, that comma-separated list. A similar example is this operator. That says, I want you to match the thing on the left, then the thing on the right, but I'm interested in both of them. So that two dots, again, that mnemonic design, that infix operator design, makes it very, well, I was going to say makes it very readable. You might disagree. When you first look at an fparsec parser, you go, so, Perl's making a comeback. So the question is, if you've got, say, a new developer coming into the company and they have to figure out what's going on, are they going to find that difficult? I think there is a danger of that. On the other hand, I think that's a danger with I think that's a danger of taking on developers who are not willing to learn. So it depends on the profile that you're looking at. So, for example, if you're in an environment where you've got a lot of turnover, there's maybe a lot of junior developers coming in, then yes, you might want to stick to very mainstream, very well understood idioms that are the sort of thing they will have maybe encountered as part of a Java course or a C# course. If you're willing to make the investment, if you're willing to say that, yeah, we believe the increased expressivity actually justifies the time that it takes people to get up to speed, then I'd be willing to make that trade in most of the companies that I worked at. Maybe I've been lucky. In fact, I know I have been lucky. That's kind of a project management issue, and it is a real issue. and it ties in with something else I was going to say later on, but I guess since you've given me such a great lead-in, I will say it now. A lot of people's reaction to seeing F# for the first time, and particularly some of these more advanced idioms like fparsec, is it's hard. I don't have time to master it. I'm not smart enough to master it. I don't believe that. I believe you are smart enough to master this stuff. How many people here have used SQL? SQL? Okay. If you're on top of SQL, then you have conquered the world. SQL is the most complicated, horrific, inconsistent language you can possibly imagine. It is huge. It has got all these weird rules. It is madness. I know F# looks weird because it's new to you. But if you can do SQL, you can do anything. Except Perl. No, I'm not trying to minimise your point there. I think that is a very reasonable point. You should be thinking about those project management issues. You should be thinking, are we able to sustain this in our organisation? But I believe that many development teams and many organisations are underconfident in their own people. You are probably taking on smart people who are willing to learn. What you need in order to learn is exposure. You're not going to get this by going to a 1-hour talk. It's still going to look intimidating. But work with this stuff, have a code base that uses it, and I think more people than we realise will actually get on top of it pretty darn quickly. I've got a lot of faith in people. So, wish me luck. How are you doing for time? Okay. Another quite idiomatic feature, which leads to some kind of interesting constructions and hopefully this time more readable constructions, is the use of partial application in F#. And partial application is something that seems quite odd when you first see it, but when you see it in the right context, suddenly feels really natural. Partial application is simply the matter of not giving a function enough arguments. Now, you can do this in C# and you will get a compiler error. Fantastic. Which sometimes is what you want. In F#, you will not get a compiler error. You will get a new function, which sometimes is really scary, but sometimes is really, really good. This is actually a big time saver when it comes to writing, for example, lambdas. And it can result in much more readable lambdas because you don't have anywhere near as much noise. So, have I got a C# example for this? I haven't, okay. So let's take a really trivial example of I want to map an increment by 1 over a list of numbers. So I've got a list of integers. I want to increment all of them by 1. I'm going to use a map or a select to do that. Well, this is pretty easy. I'll define my increment by function, and that's how I'd use it in the C# style. I'd write a little lambda, x goes to increment by 1x. Well, that's okay. That's not insanely hard to understand, but in F#, I can write that. Even though increment by takes 2 arguments, what I can do is just supply the first one, and that will leave me with a kind of dangling function that's kind of, it's been pre-programmed with the 1, and it's just waiting for another argument. So if I define that in F# interactive, and then I go, you can see that increment by 1 is a function that takes an integer and returns an integer. Increment by was a function that took 2 integers and returned an integer. Increment by 1, I've created a function that's kind of got that first argument filled in. It's just waiting for that second argument. And I can reuse that partially applied function again and again. We're a little bit short of time, so I'm not going to go into too much detail on this, but in addition to this simplifying to reducing the amount of noise in lambdas, This is also handy for sort of doing partial evaluation. So you evaluate one of the arguments, create a closure that wraps it up. It's pretty similar to doing lambdas or anonymous delegates in C#. It's just a little bit of a more compact notation. And again, it helps with these kind of internal DSLs. An example of this might be, let's take the list.map function. You can see that list.map takes two arguments. It takes the function to map, this is equivalent to select, it takes the function to map and the list to map it over. This little operator just says, take the thing before me and pass it as an argument to the function after me. So how does this little construct work? Well, list.map square is a function. List.map takes two arguments. I've only given it one. So effectively I've created an anonymous function of mapping square over. And now test values is going to be given to that mapping square over anonymous function as an argument. And because each of these is a function that takes one argument because of partial application, I can take that one thing, I can pipe it into the next thing, I can pipe it into the next thing, and I can carry on for that as long as I like. And that gives me a very link-like syntax for composing functions. It means that I can write these long chains of application in a way that goes top to bottom or left to right, rather than in-out style, as it would be if I had to go, if I had to sort of put test values on the right and then put stuff around it in the usual way of applying a chain of functions. My favourite feature is the one that you've seen throughout this. It's pretty much impossible to write F# without using pattern matching. But pattern matching is so much more than I've shown you so far. I want to go back to my expression node example. And suppose I want to write a little diagnostic function that gets the depth of an expression. So how deeply nested are the expressions? Well, unfortunately, there wasn't a depth method in the abstract base class. The person who wrote that, the dumb bearded fool who wrote that, didn't anticipate anyone needing to get the depth of an expression. So in order to do that, in order to implement that, I have to do this whole pile of casting or type checking, and I have to dive into the details of each individual case. And you know that when you see casting happening, it's a bit smelly. You kind of want to get rid of it. It's certainly quite verbose to follow. Well, as we've seen with pattern matching, you don't need that long, complicated stuff. You've got these cases already there for you, and you can write it in a much more concise way. Pattern matching not only matches which case we're in, but it also decomposes it, pulls out the data associated with that case, like the variable name or the numeric value or the list of function arguments, so that you can handle those on the right-hand side. We can also pattern match on records. So there, although I've not mentioned point3D, if I go look at that, you can see F# has inferred that takes a point3D, and it, by putting this as the argument form, I don't need to use the dot notation. It gets decomposed automatically. A nice feature of this is using tuples to return multiple values from a function, and you can then capture those into variables in a single statement. So here is one of my arch nemeses, the dictionary.try-get-value method, which in C# use out parameters to get results from that, and it's quite fiddly to work with. In F#, the language itself goes, well, we don't like out parameters because they involve mutation, so what it's going to do is return a tuple. It's going to adapt it to return a tuple of a Boolean and the found value. And I can then match the found value, or I can just match the tuple directly. So I can go, I want to match the result of try-get-value. It's either going to be true and a value, or it's going to be false, and in that case, the other parameter, the other return, is nonsense and I can't use it. So you've got this very concise, very expressive, very declarative way of handling all these diverse situations. And in fact, you can extend that system with a feature called active patterns to add your own ways of recognizing and decomposing and classifying data values according to your own required logic. Those are my kind of big 10. Well, they're my kind of medium 10. There's some small features I like. There's some big features I like but don't have time to go into. For example, one little feature that I find kind of cute, kind of helpful at times, is something called object expressions. And an object expression just allows you to implement an interface or indeed just a member on an object. You don't need to create a whole new class. Just go, I want an I-equality comparer that behaves like this. And you can declare those functions in line. So see here, I'm not declaring a whole new class for this. I'm just saying, pass me in the digits, pass me in the number of digits to round to, and I will return you an I-equality comparer for decimals. No need for a class, just declare the members directly, the members of the interface. Triple quoted strings. This is such a tiny, tiny feature, but when you want it so badly. If you ever have a string that you want to put double quotes into, a literal in your program that you want to put double quotes into, just build an F# project to put that one string into. It's just easier. Units of measure, as famously not used on the Ariane 5 project. In F#, you can define these measure types, and you can declare values as being typed. So there's some types. So now I can figure out how long does it take for light to get that distance. And you can see down there, firstly it's quick, but secondly F# has figured out that that is in seconds. It's not just a plain floating point number. It's actually got a unit associated with it, and F# is preserving those units as it goes through. Which means that, hold on, I'm getting to the Ariane 5 case. Which means that if you have European and American teams collaborating, and they write something like that, then when somebody, probably the Americans, writes, what's that? I'm awfully sorry. Any Americans in the audience? I do apologise. I love you guys. Which means that I'm actually going to get a compile time error saying you can't subtract feet from meters. You need to actually put a conversion there. Just to be clear, this is not a system that is aware of conversions. It's not got some kind of built-in concept of what the various units are and how they convert from one to another. All it's doing is dimensionality checking. If you want to convert feet to meters, you have to go ahead and write a function to convert feet to meters by doing some fancy arithmetic stuff. I don't know. What else have we got? F# Interactive, you've seen me using that. Did anyone go to Glenn's Script CS talk yesterday? Yep. So F-sharp Interactive it's a bit like script. It doesn't have some of the really nice features like NuGet packages and script packs and stuff like that. One plus side, though, is that it's built into Visual Studio. There it is down there where you can't see it. And you've got the handy features. If you're working on an F-sharp program in Visual Studio, you can just hit Alt-Enter at any point to send the selection to F-sharp Interactive to have it evaluated. So it enables a very exploratory style of programming. Something that Glenn told me about yesterday is that the Script CS guys, there's a couple of F-sharp community members who are working on integrating F-sharp into Script CS. So we'll kind of get that best of both worlds of F-sharp Interactive plus that NuGet integration, which is going to be pretty awesome. There's also a utility called Tsunami, which has that feature too. Active patterns I mentioned, so the ability to extend that pattern matching system. Type providers, which allow you to eliminate writing a lot of boilerplate code. A nice example is the regex type provider. There's a really bad regular expression for New Zealand phone numbers. Notice that I've named some of the groups, and now when I use a match of that type, I can get IntelliSense to remind me what those groups are called and to give me a compiler error if I get the name wrong when I try to use it. And I've not had to write any wrapper code to do that. The F-sharp type provider has done that for me. There's another one, for example, that looks at SQL databases. So again, none of this dragging things into entity framework or linked SQL or whatever. Just point to a database, get your classes, no problem, until someone changes the database schema, at which point you're hosed. And there's a powerful feature called computation expressions, which is about a 3-week course in and of itself. This has been used to implement async, C# style async in a library long before C# had it. Another feature that's been used for is the ability, for example, to write code in F#, compile it down to CUDA kernels, and run those on the GPU as native CUDA code. So we had a bit of a discussion earlier about some of the dangers of this. I appreciate people have got a lot of investment in C# and Visual Basic. You're not going to throw out your existing code base. You're not going to rewrite everything. F# is a product to be used where it's appropriate, where you see value, where you see benefit, where you think that the benefits outweigh the risks. You do not need to throw away what you have. I don't really have time to show you much, to really show you the interop, but F# compiles down to IL. The methods that you've seen, the functions that you've seen, compile down to IL methods. You can call them from C#. The libraries are .NET libraries. They will interoperate fine with C#. Some of it is a little bit fiddly. Things like the list types are quite fiddly to work with. Dealing with discriminated unions can get a bit, you want to write quite a few helpers. There's a library called F#X, which you can get from GitHub. If you're interested in doing interop, it provides you with a lot of utilities to help with that interop that will make it much more seamless for you to do that stuff. But it works really well. I've done a couple of projects, one of which was a calculation engine, a reporting engine where users could enter their own formulae. We did all of that parsing and evaluation in F#, and it was called from a C# WPF application. I worked on a product called Web Workbench when I was at Mindscape, which does language integration to Visual Studio. We did all of the parsers for that and all of the semantic checks in F#, but all of the Visual Studio integration side was done in C# and called into the F# library. And it was pretty much transparent. So find the options, find the opportunities. Look at where the things I've shown you will help you, will actually make your code easier, and consider using F#. There is a learning curve. There always is. I would encourage you not to be frightened of it. It's not as hard as it looks. No language is as hard as it looks at the first glance. All languages take some getting into. But once you work with the code, it does actually become quite natural. The more you practice, the more you do. There are huge payoffs to this thing. These things like pattern matching, partial application, these custom DSLs give you the ability to write really expressive code really quickly and once you're used to it, very readably. Don't rush out. I'm not saying rush out and change your code base. That would be unrealistic. But there are areas, there are projects that you're going to take on in the next few months where F# is going to be a better fit than C#. Not your whole project, but because you can interopt, you can call out those bits, build them as DLLs, build them in F#, call them from your main project where you've got all of the tooling, where you've got your existing code. It works really, really well, and it pays off really, really well. Try F# on the web. Have fun. Thank you for your time.